Okay, so today let's start discussing about no degenerate perturbation theory. Okay, so the method, whatever we are following, is exactly the same like non-degenerate perturbation theory, but we have a limitation when we are doing that approach directly, and we have seen that some of the limitations we have discussed before is the major limitation is nothing but the divergence of the wave function or energy solutions when two different states are having same energy. That is psi n. Yes, according to the perturbation expansion, psi n we obtained it as phi n plus the first term, and we can write it as sigma m not equal to n phi m hp phi n divided by en0 minus em0. So this is the expansion, and it will keep on going like that. The moment any two energy states are going to get equal, if it is equal, this quantity is going to be 0, right? Two different states are there and both of them will be equal to 0. And if it is a in the numerator, if we have any finite number, the entire term is going to be infinite. Some finite number divided by 0 is going to be infinite, and the wave function is going to blow up. There is no wave function which is going to infinity at any point. So that is a condition for our wave function. So that kind of a solution is not possible for us. Okay, so we have to do some sort of changes in the method to incorporate the degeneracy factor. Okay, so ultimately what we have to do here is to find out the solution exactly like before. H psi n equal to E n psi n. So the psi n is nothing but the unknown wave function that we have to find out. Right, the psi n is something that we have to find out, and of course the n energy and values. And the Hamiltonian is for the unknown problem, and that Hamiltonian we can split into two parts: h naught plus an hp component, it's a perturbing component, and both of these will act on the wave function, and it'll, yeah, you know how we usually do that. So for solving this perturbation analysis, one thing that we need to know is to have a known solution or a known Hamiltonian and a known set of states. So okay, so the known problem for me here is as before. It's h naught phi n equal to en naught phi n naught. So the phi n naught is not required. Phi n is always the unperturbed state in our representation. Okay, so this is the unperturbed state. Phi n is the unperturbed state or non-problem for us, non-thing for us, and we have some speciality of this space. We have taken space as orthonormal, so phi n phi j phi I phi j equal to delta ij, and the completeness condition also valid. M phi m gives you 1. So this is actually an orthonormalist basis on which we are representing our unperturbed state of the Hamiltonian. Okay, now yeah, for solving this, what we have done, we just taken this wave function, okay, the non Hamiltonian corresponding to that non wave function psi n is taken as something like phi n. It's an unperturbed state of the same thing plus lambda, and we will expand it in terms of lambda. You'll be getting psi n1, it's a first order correction, and etc. It will go like that, and our energy and values also same way will be expanded in the powers of lambda en0 plus lambda en1 plus etc. like that. And we will just put the operator on top of the states, and you will find out the you will compare the lambda terms and you'll find out the equations. That's what we have done. In this case, our unperturbed state phi n is degenerate. So phi n in this case is degenerate. That is our unperturbed state. Phi n is degenerate. Well, if phi n is degenerate, what happened? What is this degeneracy factor has to do? Okay, so when there is a degeneracy, then what will happen? Let's see. Okay, I have to put that degeneracy factor directly into the representation. So phi n is the nth state of phi. It can take any value. I am taking that phi n here with okay, and I am putting another subscript here to represent my degeneracy as well with that seed. So alpha here represents the degeneracy, and the alpha can run from 1 to 3 etc. up to f. F is the maximum degeneracy. So okay, so to illustrate what happens here, phi n, let me take state 1, and I want to see what are the possible degenerate states for this particular phi 1 state. So that phi 1 state is having, if there is a full degeneracy, this will be having phi 1 phi 2, sorry, phi 1 phi 1 etc. etc. It will go up to phi 1f. These are the different degenerate states of phi 1. Okay, so as you know, it's a degenerate states. It's kept acting on the any of the states. All of them will produce you en0 or even 0. Even you can write 0, yeah, since it's not, let me write it as en0. Okay, and it's not acting on this state, it will produce en0 into phi 1. On this state it will produce phi 1, and in this state it will produce phi 1, and phi 1 of as same way. So this is the way this is acting, and all of them are having same energy value, ion value. That is the reason we are calling this is degenerate case. Okay, this is true. And when we are writing phi n here, or we want to write the representation of phi n, well, we cannot just take any of the state. We have to take or the phi n representation here should have all the components which are there inside that particular degenerate state, right? If you exclude anything, it means for example you are calculating the state of en0, so you just want to calculate what are the states that en 0 corresponds to. If you want to answer that, your wave function corresponds to that state should have all the information about all possible states. And you know how to do this. We have done in the case of identical particles, and sort of yeah, we have done several times. So this is nothing but it will be a combination of linear combination of all these states. So that is how we represent this phi n alpha state. So phi n, yeah, phi n alpha is this particular subspace of phi n, you can see. Okay. Yeah, so phi n, if you want to represent, this is nothing but just noting from here itself, phi n is nothing but it should be a combination of some linear combination of a constant a, alpha, phi, this is n alpha. It's a combination of where alpha is running from 1 to f, if f is the degeneracy of that state. It can take any value, so it will be a combination of all the possible values. Okay, so this is something that we know now about the degeneracy, and we have according to perturbation theory, what we will be doing, we will be finding out the correction of first order correction. Okay, lambda power 1, if you want to compare, what you supposed to do, you have to what we have to do is we have to put the correction or the perturbed Hamiltonian on the basis first order correction. If you want to calculate, how do you do that? You don't put the h naught here, you put h prime or hp. hp is including that lambda, so hp is going to act on these old states now to find out the correction. So hp is going to act on phi 11, phi 12, phi 13, and so on. Now when hp, it's not h naught, if hp is a perturbed Hamiltonian component, is going to act on some state, and in that case it's not necessary that it has to produce the same energy correction, or it has to do the same sort of process for all the states, right? It can be anything. The perturbation can do different things on different states. It can be same, but not necessarily the same. If it is not same, that is going to be in mostly the cases. Some cases, some of the states will be having a similarity, but otherwise no. So if this is not the, in general, they need not to be same. So in that case, it will be just like E1. Okay, it's not 1 0 anymore. You have to specify which state the energy corresponds to. So E1 1, right? Alpha corresponds to 1. This is the first order correction, and it will produce phi 1 1. Similarly, E 1 2 1 phi 1 2, and E 1 this is, and this is 1 3, etc. Similarly, phi 1 3, and so on. So the main idea here is that, see, the way we are finding out the correction is by putting, okay, you know that first order energy equation, that is nothing but phi n h prime phi n. You are applying the perturbation component on the unperturbed state. That is how you find out this lambda power 1 correction. So that way you are putting the perturbation on the degenerate state, and you can have different eigenvalues uh, yeah, it can have different values, as you can see here, not necessarily the same. So what it means is that what happens here now, let me just take that the my problem, my unknown problem, or the problem that I want to solve. H uh, is nothing but H naught plus HP. It's a combination of these two states, right? So if I take that particular component H naught plus HP, what happened now? You can see first state is En naught, and uh, if you are taking it associated with 511, E10 is there, uh, unperturbed component, and this component will be adding as the first order correction into that particular thing, and this will be added along with this, and the third one, this component will be added. If they are not same, uh, if you do this H is your final Hamiltonian that you need to find out. H on this state phi n alpha, it's not going to produce the same value for each one. There will be energy differences if you compute the H. Because of this factor, there will be energy differences between the states. Now, what does it mean? If the energies are different, that means the degeneracy is not there right now. So the moment perturbation is acting on that, degeneracy is getting lifted away, and that's the way you call that lifting of degeneracy. So this will happen, this can happen. Not necessary that all the degeneracy will be going. It depends upon the root of this quantity what we are getting. If all these quantities are same, you can see, oh, there is no degeneracy lifted away. All this quantity what we are getting is same, then there is nothing, no change. All the states are having again same sort of energy, and degeneracy is not taken away. Otherwise, the degeneracy is lifted away. So in general, perturbation acting, this is the change that is going to happen for the state, that the degeneracy can be lifted away, and yeah, so energy corrections, it will be splitted into different energy, different possible energies. So okay, yeah. Now what we have to do is, you know, this phi n is actually an element of a Hilbert space, and that n values there in that bigger Hilbert space, we have n varying from 1 to whatever that number, depending upon our problem. Now you can consider this phi n and the associated degeneracy components as a subspace of that bigger space associated with phi n. So the phi n itself is composed of three different states in this case. It is composed of whatever number of degeneracies there, that many components along with that. So this can be taken as a separate or a subspace of the larger space, and you can consider, okay, this is actually, you can take such kind of a subspace, so we will be taking it as a subspace, and in that subspace, let me take, let all these components are orthonormalized. So this is something that I'm taking. I'm assuming that this is, all these states are orthonormalized on the subspace. If that is the case, again we have the condition like phi a particular state on the larger space, and this is a degeneracy factor coming in. So I put I phi n j equal to delta ij, right? And also, if you want the completeness rule, the states are running from alpha equal to 1 to f, phi n alpha phi n alpha is equal to 1. So this is because of our consideration that the space that I am forming, or the subspace, is orthonormalized, and you can take it all the time. But the space is having some speciality that you will be, or the spaces are having some speciality that we can see later. Okay. Now, what to do now? Okay, so yeah, the next step is again like our non-perturbed. It's actually a similar process, nothing but comparing exactly the same formula for non-perturbed, uh, so non-degenerate perturbation theory. Okay, so you know how to get the lambda power 1 equation and compare it. So the lambda raised to power 1, if you compare lambda power 1 terms on that equation, I ultimately what I need to find out is two things here. One is the first order energy correction, and okay, I need to find out this phi n, that is my state now, and I don't want to go to the first order. I just want to find out zero order correction. I'll be very much happy. We will be discussing only till here. Just want to find out the coefficients of this a alpha. That's our discussion. We will not be going to the first order correction in wave function. So we will be going to the first order correction in energy and the zero order correction in the wave function. So zero order, we need to know this a alpha parameter here. So a alpha parameter, okay, let me just write this. If it is normalized, if you take phi n, like, I just want to find out the scalar product phi n phi n. This phi n is nothing but your sin 0 kind of unperturbed component, right? Sin 0, so that is nothing but sin. This is something that we have taken now as well, sigma alpha 1 to f. Oh, okay, you have same component, so that's nothing but a complex conjugate, it will come, and a alpha complex conjugate multiplied with a alpha, and their corresponding term, that here in this case it's like phi n alpha and phi n alpha, and this is nothing but delta that's nothing but 1, right? It's orthonormalized. Okay, so this is nothing but the square of this term, and if it is normalized, this is nothing but sigma alpha equal to 1 to f a alpha square. So the coefficient square are going to be equal to 1 if it is normalized. That's something that we already know. We have seen it several times. What it means is that the a alpha here corresponds to the probability amplitude of a particular degenerate state, right? So if there are 10 states, and how likely one state is going to arise is having this that is being associated with this particular quantity. Okay, so what we have to do our non-degenerate perturbation theory is to